So, 1820, Hans Christian Ørsted giving a public lecture about current events in physics. And one of the current events was, ironically, current, and the other was the Earth's magnetic field that a person named Gilbert had figured out that the Earth was a giant magnet. And so Ørsted had compasses for talking about magnetism and the magnetic field, and he had wires that he was sending current through. And some people would say, Danes especially, that he was very intentional about what he did. I think most people say it was an accident. But the important thing was that when the accident happened, Ørsted recognized his significance. So he had a compass sitting on the table, and he had wires on the table, and he sent current through the wire. And it's very important that the wire cross the compass correctly. I will show you in class that if the current is sent like this, which you might think is the ideal way, nothing noticeable happens to the compass. However, when the wire was this way across the compass and current was sent through it, the compass needle changed its orientation, which clearly indicates that there was a magnetic field, different from the Earth's magnetic field, created when current went through the wire. Suppose instead we had the wire going underneath the compass. What would you predict in that instance? Would it do nothing? Would it do the same thing? Or would it do the opposite of what was there before? And it turns out that when the wire is underneath and you send the same current through the wire, that the result is that the needle turns the opposite direction. So we need to see, just on the basis of that, the fact that there is no response when the wire is going perpendicular to the orientation of the compass, and that you get maximum response when the wire is going parallel to the orientation of the compass, and that it goes opposite directions, whether the compass is above or below. We want to see what that means about the magnetic field. But before we get to there, I need to establish a convention for how we're going to draw a three-dimensional event. I want you to think about a wire carrying current like a pipe, and the current, of course, we represent with an arrow, but this time I want you to add feathers to the back of the arrow. And if you look down that pipe, which is extending towards you through the page, and you see the point of the arrow, then the current is approaching. And if you look down the pipe and you see the feathers of the arrow, then it's going away from you. All right. With that established, I want to consider, here is a current coming towards you, and I put a compass above the current, and there is a, come on, just go away. There is a magnetic field to the left, And when the compass needle is under the wire, there is a magnetic field to the right. And here, for a current, the direction of the field, or the direction of the current, is the direction positive would go. For a magnetic field, the direction is the direction a north would go. We have the choice of north or south, and we choose north. Why? Because it's all the Europeans are up in the northern hemisphere and they think they're the most important and that they should be at the top of the map. Okay. Now, based on the fact that here at the side we don't see any magnetic field out of the compass, and we see these kind of magnetic fields on the two sides, what do you think the magnetic field looks like? And I would suggest that the magnetic field encircles the wire. So I can pull these down a little. That the magnetic field goes around the wire like this. And indeed it does. And if you send the current in the opposite direction, the magnetic field goes in the opposite direction. So you need to know that the magnetic field around a current-carrying wire encircles the wire, and then to get the direction that it encircles it, we have the first of many right-hand rules. And again, why the right hand instead of the left? Because right-handed people dominate. So, if you take your right hand and make a loosed fist, then your thumb points in the direction of the current and your fingers wrap in the direction of the magnetic field. You ought to try that out on this. That is, take your fist, a loose right-handed fist, point your thumb towards you, and see if your fingers are not going around as indicated by these arrows. Here is a photograph that was made with a horizontal piece of paper, a current-carrying wire going down through the center, and then they sprinkled iron filings on the paper, and the iron filings, because of the magnetic field, get magnetism induced in them, and they line up with the magnetic field, which you can see encircles the wire. And further, if we were to put some directions that they go, you should be able to tell me what direction the current is going through the wire, and you will on your worksheet. Now, in the effort to take a long wire which has magnetism around it and get more magnetism to intensify the magnetism, what we can do is take the wire and coil it, and then all the magnetism will be added together in a small area. That's intensity. And when you do that, when you coil wire to get a strong magnetic field, this thing is called a solenoid, which, by the way, has the word sol in it. You can also call this shape a helix, which has helios starting it off, both of which refer to the sun. What does this crazy thing have to do with the sun? And if you want the answer to that question, you should take astronomy. Okay, so I have this coil of wire, and I'm going to cause current to flow through the coil of wire. And what you can see is that with the current going that way, if you take your loose right hand, fist, and point your thumb in that direction, you get your fingers going around like this. Back here, you point your thumb in the direction and your fingers are going around like that. And here. the magnetic field encircling the wire, and the magnetic field encircling the wire, and the magnetic field encircling the wire. Please notice for all of these that up through the center of the coil, the magnetic field is going upwards, and down around the outside, the magnetic field is going down. That the magnetic field for this coil of wire, this solenoid, is going to go around the wire so that it's going all the same direction through the center and the opposite direction around the outside. Now, to predict that direction, we use the same right hand that we were using before, but we're going to give it a new name. We're going to call it curly straight. And when the straight is current flowing in a wire, then the curly is the magnetic field. But this time, the straight is the magnetic field going through the center, and the curly is going to be the current flowing around. So here you see it again. There is that same loose right hand fist, but now the straight element is the magnetic field, and the curly is this current which is flowing around. And your thumb indicates the direction of the magnetic field through the center, but it also indicates the direction of the magnetic field coming out of this end. And because the magnetic field goes away from that end, we call that the north end of the solenoid. It is the end that pushes north away. And this would be called the south end because it is the end that attracts the north. And that's what we do with magnets. The end that pushes north away, we call the north end of the magnet, and the end that attracts south attracts north is the south end. Okay, so let's apply it. You do this problem. Now, I want to establish an idea. When you put two magnets with like poles together, their magnetic fields, again, the field goes away because north is repelled from the north end. When you've got fields, adjacent fields going in the same direction, that results in a repulsive force. You know that a north and a north repel, but what I want to get at is adjacent field lines in the same direction is repulsion. And here, where you would get attraction, note that you have adjacent field lines in opposite directions. Granted, what's going to happen to this is it's going to transition to have the field look like that. But prior to that transition, adjacent field lines in opposite directions, that's going to be an attractive force. Okay, now, applying that idea to this problem, I've got two different magnetic fields. I've got the magnetic field that comes from these, what we call field magnets, these permanent magnets out here, that's in green, and I've got the magnetic field that results from this current carrying wire, and that is in red. And if they are in opposite directions, then that would result in attractive force. And if they are in the same direction, that results in repulsive force. So go through these 4 pictures and figure out which one indeed has the red curly in the right direction and has the magnetic field in the right direction and has the force from that interaction in the right direction. This is a current passing through a magnetic field resulting in motion. That is a motor. And that is the basis upon which you are going to build your motor. But more on that later. Go back to previous things we have learned. When we were studying work, it was the dot product of force and distance. That we were only interested in the parallel components of the force, and so when you do a dot product of two vectors, the result is a scalar, and the magnitude of that scalar is the magnitude of A times the magnitude of B times the cosine of the angle between them, because you're only interested in the parallel. You're only interested in the parallel parts. Whereas when we did torque, the result of multiplying two vectors was a vector. So it's a vector product or cross product. And there you were only interested in the perpendicular components, and so it was AB sine theta. So the magnitude was given by this, but there is an issue. What is the direction of that vector? After all, what we have done is taken current, which is a vector, and magnetic field, which is a vector, and the result is a force, which is a vector. So it's definitely going to be a cross product of those two that we are going to do. And here it is. With cross products, unlike dot products, it is not commutative. It's very important that you have current first and magnetic field second. And just as we did for getting the direction of a torque out of these two vectors, so too we're going to take your right arm, sorry lefties, and point your right arm in the direction of the first vector, and then turn your wrist until you can wrap your fingers into the direction of the second vector, and then your extended thumb points in the direction of their product. So this will be the way we will get the magnitude, and this will be the way we're going to get the direction, both of which are important. And the actual formula is IL cross B. But so if you're actually calculating the magnitude, don't forget to put the length of the wire carrying the current. But this will be fine for getting the direction of the force. We can leave the L out. And so we go back, and in the previous problem, you should have, I was doing it wrong. We should start, and everybody should do this. Take your right arm and stick it behind you, so it's pointing in the direction of the current. You must start with the current, and then turn your wrist until you can wrap your fingers to the left. That is, in the direction of this magnetic field, which would go from north to south, and your thumb should be pointing up. And that is the way, not this magnetic fields in opposite directions and adjacent magnetic fields in the same direction. No, we're going to use this rule here to get the direction of the force when a current happens in a magnetic field. Okay, so you please do this problem. Again, capital B is the symbol for a magnetic field. Should have said that earlier. Here is the velocity, but it's a positive charge. So from that, you ought to be able to figure out what the direction of the current is. Remember to start with the current, then wrap into the magnetic field, and what direction is your thumb pointing. And then you can do this problem, and I would remind you that the magnitude is IB sine theta. Actually, it should be ILB sine theta. But what is the theta between these two? And finally this one, which is a little bit awkward because I've given you the force and asked you to figure out the magnetic field. Into what direction would you wrap the current to get your thumb pointing in that direction? And that is the end of the show.